Hello, my name is Max Gambetta, and I am from New York. My experiment is encoding colors in a quantum computer. In a camera surveillance system, the efficient use of feature selection in an image is required. One of the main forms of feature selection is color selection, which utilizes RGB values of a video or image. Image recognition via color selection on a classical computer is inefficient, however. A quantum computer may be able to utilize color selection more efficiently due to its different way of computing data, however, and therefore making it more efficient than the classical computer. In my review of literature, the goal of the first article was to study the necessary requirements for classical computers to keep up with the increasingly more powerful AIs. What they found is that the amount of computational power used to train the largest models had doubled every 3.4 months since 2012. This is a major reason why quantum computing is required in order to keep up with the growing power and requirements to run AI. The goal of my second article was to build logical qubits for a quantum computer that are able to balance coupling and control with coherence. What they found is that classical computers do not have enough power to run quantum problems, and that the new quantum computer can. With logical qubits, the future quantum computers would allow for very efficient computation. The goal of my third article was establishing quantum randomness, and to also establish the difference between a qubit and a quantum bit via this randomness. What they found is that if a coin was flipped twice on a classical and quantum computer, the program would give a 50-50 chance for the classical to be either heads or tails, but for the quantum, it would give a 99.3% chance of it being one side over the other. What this means is that the randomness was undone, showing that qubits are different from classical bits because of their ability to undo randomness. The main problem of my experiment was to see if color encoding can be done more efficiently on a quantum computer than on a classical computer. I think that if color encoding is used in a quantum circuit, then a quantum computer can encode more efficiently than a classical computer, and I hope to encode color in a quantum computer and test if color can be encoded more efficiently. In my experiment, the role of student versus mentor was for the student to create a quantum circuit for color selection, create images for use in testing, test the computer's color selection capabilities, and create new tests for the computer. The role of mentor was to provide student with access to scholarly journals and articles, assist with the construction of quantum circuit and programming, provide students with resources to learn about the topic and gain expertise, and provide professional opinion on work. In my methodology, the first step was quantum computing over the cloud. In this step, the tools and requirements are reviewed. What you will need is a computer or a laptop with the Qiskit software developer kit installed, access to the IBM Quantum Services. The IBM Quantum Services provide real quantum computers that can be programmed over the cloud. You then want to use a system called Bogata. Bogata is a 5-qubit system. When selecting the best qubits on Bogata, qubits 3 and 4 were used as they have the best T1 T2 values. Higher T1 T2 values mean more efficient and accurate experiments. You can see the T1 T2 values on the figure 5 on the right here. Step 2 is representing a picture via pixels. An image was broken down into pixels, and each pixel was represented by a qubit. The images are broken down into 2 pixels labeled qubit 0 and qubit 1. When selecting the colors for testing, the colors of the Roy GBIF were selected. These colors are red, orange, yellow, green, blue, indigo, and violet, as well as 3 color combinations of these colors. You then collected the theta values using a function called RGB2point. This function calculates a different theta value for each color. Step 3. The quantum circuit for encoding color. The quantum circuit for encoding color is shown in figure 8. Each qubit represents one of the 2 pixels, and the value of theta in the phase gate P for both pixels is set by the function RGB2point. The experiment was then ran for 10,000 shots to ensure accurate statistics, and the phase was measured using another function that converted the output of the quantum circuit into an estimated phase. The estimated phase will be compared to the measured phase in order to allow for a percent error between the two to be deciphered and uncovered. Step 4. Quantum circuit for true colors. Representing a true color. To show that a quantum computer can encode and measure all colors, the true color image was used. This image was converted into 20 pixels, and each one of these pixels was 96 points apart, as shown with the black lines. The values for theta were obtained in the results section and will be discussed later. The left figure shows the encoded and measured theta values for the true color image. As you can see, the 1.94 for encoded and 1.9453 for the color violet are very close in number and have a percent error of about 0.3%. This is very good, as it means that quantum computers can encode color very efficiently. You can also use these theta values to estimate colors. For example, 1.94 to 1.36 would be a good range of where you'd find the color violet, while 1.14 to 0.01092 would be a good range of where you'd find indigo. The next results part is the single color encoding, where both sides of the image were one color. As you can see, when comparing the encoded theta and measured theta, yet again, there is a very low percent error of 0.2%. This shows, yet again, that encoding colors on a quantum computer is highly efficient. In the final results, the two color images were selected, where each image is a different theta value, meaning the compute theta values can be used to tell the difference between colors, and the two colors are close with about a 0.25% error, meaning, finally and yet again, that color encoding on a quantum computer is highly efficient. Discussion. RGB values have a unique theta value, and all these values can be mapped on a color wheel. The different numbers are referred to as theta or an angle, and these can be encoded into a single qubit using quantum phase with a phase gate. When comparing a classical bit to a qubit, only one color can be encoded per bit. True color needs 24 bits. A single qubit, however, can be used to encode true color. This means that a single qubit is at least 24 times more powerful than a bit. Comparing colors. Via breaking the picture into pixels and each pixel being a qubit, one can tell if an image is blue/red, orange/indigo, or yellow/violet. In the final experiment, all colors were encoded into a quantum computer by breaking up an image of true color into 20 pixels. From the measured value in the first experiment, one is able to estimate the color and agree with the image that was used for encoding. In future research, I would like to implement machine learning into a quantum circuit, use existing color data to train the quantum computer to use machine learning to recognize the data as patterns, and I would like to do repeat tests to verify the pros and limitations of machine learning while encoding on a quantum computer. In conclusion, the potential implementation of future data sets in order to test the capabilities of machine learning paired with a quantum computer is what I want to study. Below is a potential circuit that I could use in this experiment. In conclusion, my problem was, can color encoding be done more efficiently on a quantum computer than on a classical computer? And my goal was to encode color in a quantum computer and test if color can be encoded more efficiently. I believe if color encoding is used in a quantum circuit, then a quantum computer can encode more efficiently than a classical computer. In conclusion, color can be encoded into a quantum computer with far more efficiency than a classical computer. My name is Max Gambetta. I'm from New York. Thanks for watching.